When the yellow tape goes up around a major incident, the environment inside that perimeter is immediately on the clock. You have emergency personnel moving through the space, vehicles leaking fluids, and structural damage settling, creating a highly chaotic, entirely temporary physical environment. The most crucial pieces of evidence on the ground are often the most fragile. Delicate tire marks, scattered debris, and fluid stains are entirely exposed to the elements. A sudden heavy rainstorm can permanently wash away hours of vital information before anyone has a chance to record it. Compounding that weather risk is the pressure of modern infrastructure. If an event shuts down a major arterial highway or a critical public facility, authorities are under intense pressure to clear the wreckage and reopen the area. Investigators have a strictly limited, rapidly closing window before the scene is dismantled and swept away by standard cleanup crews. To beat that clock, investigators rely on a highly specific digital workflow. This diagram illustrates the solution: digitally freezing the physical space. By splitting the environment into 3 distinct data streams, we capture the scene from the air, measure it with lasers, and record its surface textures. Modern forensics focuses on permanently digitizing the exact spatial reality of a fleeting moment in time. This allows experts to walk back into that specific afternoon, years after the asphalt was washed clean. To see how this works in practice, we have to start at the macro scale. Looking at this top-down schematic of a sprawling highway crash, you can see debris fields stretching for hundreds of yards across multiple lanes of traffic. Walking through a site this large risks disturbing the exact evidence you are trying to find, so the first tool deployed is an automated drone. Flying overhead in a precise grid pattern, the drone maps the overall geographic footprint of the area before a single boot touches the ground. This grid map shows exactly what the drone is looking for, actively calculating vector relationships between distant points. It measures the exact distance from where a skid mark begins to the primary point of impact to the vehicle's final resting positions. By locking in those wide-angle coordinates from above, aerial macro mapping provides the foundational geographic borders. It creates the digital boundaries necessary to ground the rest of the accident reconstruction. Once the outdoor borders are set, investigations often shift inward to the mesoscale. If a sequence of events moved inside a building, investigators need the precise structural dimensions of ceilings, walls, and interior corridors. LiDAR uses a central spinning mirror to fire millions of laser pulses, measuring the exact fraction of a second each beam takes to bounce back. This instantly generates a dense point cloud, mathematically rebuilding the room into geometric coordinates to verify exact physical trajectories. Because it relies on light pulses rather than a camera lens, LiDAR generates a high-precision geometric skeleton of the environment. The resulting dataset remains consistent, providing a fixed structural reference that remains independent of human interpretation. But LiDAR has a blind spot. While it maps physical shapes with high accuracy, a laser beam cannot interpret color, it cannot read 2D patterns, and it cannot see visual textures printed on a flat surface. That becomes a major problem when we drop down to the microscale of an investigation. Proving exactly how an event occurred often relies on analyzing the precise shape, color, and distribution of microscopic details, like bloodstain patterns along a baseboard. To capture that detail, teams use photogrammetry, the process of taking hundreds of high-resolution 2D photographs with heavy overlap. Specialized software scans these images, identifying shared pixels between frames to algorithmically calculate depth, extruding those pixels into a unified 3D texture map. If LiDAR provides the mathematical bone structure of a crime scene, photogrammetry provides the essential visual skin required for deep, microscopic forensic analysis. These tools rarely operate in isolation. Consider a complex scenario where a commercial vehicle leaves a roadway and crashes into the side of a building. Solving that requires macro, meso, and micro investigation all at the exact same time. First, the overhead drone map locks down the macro environment, plotting the curve of the road and the path of the vehicle. Then, as this diagram illustrates, the interior structural geometry from the LiDAR and the high-resolution surface textures from the photogrammetry nest perfectly inside those drone map coordinates. The data layers collapse into a single model. Merging these completely independent datasets creates a digital twin of the environment. Investigators are left with an investigative asset that entirely eliminates gaps in spatial context, allowing them to examine the scene from any conceivable angle. Ultimately, the most rigorous digital investigation means nothing if it cannot be understood by a jury. Fast forward months, or even years, after the debris has been cleared, and the final destination for this data is the courtroom. Historically, presenting spatial evidence meant handing the jurors a stack of flat, disjointed 2D photographs and a few hand-drawn maps. Juries had to mentally piece together a complex geometry that they had never physically walked through. Today, lawyers project the full 3D digital twin directly onto courtroom monitors. As you can see in this rendering, they can smoothly shift the perspective from a bird's-eye view down to a specific first-person eye-level coordinate, allowing the jury to virtually navigate the true spatial layout of the day in question. This level of mathematical accuracy provides a fixed reference for the trial process. If a witness describes a specific vantage point, the model can objectively verify that perspective, grounding the courtroom debate in the original dimensions of the scene. These digital environments turn fleeting physical evidence into a permanent record, linking a chaotic past event to a data-driven verdict in the present.